the thing that I want to kind of introduce now are different applications of convolutional neural networks, convnets. The sort of ones that grabbed all the attention last year, so starting with Deepdream, because this is kind of where I think a lot of people from, let's say from the creative coding community began to get really interested in applications of machine learning. So I was just going to show you some kind of really weird psychedelic images that convnets are capable of creating. And with this, I'm going to also show you some of the more like experimental methods that are in the research, which may not have very obvious creative applications, but I think if you think about it, you'll see that they might be actually very useful in the sort of toolkit that we have. And while we go, I'm going to try to make reference to different repositories that have implemented this stuff, because if you're interested in using them, there's a lot of people here who are pretty capable we already have some of the deep learning stuff installed. So I think we'll be able to kind of use this stuff pretty easily. A lot of them are command line tools. They're actually quite useful. Okay, so last year on Reddit in June, there was this, you guys know Reddit, right? There's a machine learning subreddit, which is actually one of the really nice spots in the internet where there's actually pretty open discussion about machine learning research. And a lot of it is pretty technical, but a lot of it is also very speculative. There's also some on Hacker News, although Hacker News tends to be more focused on like, startups and VC type stuff, and the Reddit channel is much more research oriented. And then basically last June, so about a year and a half ago, someone posted this anonymously on the main channel of Reddit, an image generated by a convolutional network. And actually, I'm missing the image itself. Let's see if I can find it. Is it this? Yeah, this thing. So this is weird, like slug-looking thing, and everyone was like, "Okay, please give us code or reference," or no one knew what it was at first. And it turns out, and we later found out that someone at Google leaked it. They never found out who it was. So what they had been working on this research for a little while that they ended up calling Deepdream, which was this approach that I'm going to explain now, which was generating these weird images. And it came out of earlier research that had been going on, which I kind of made reference to yesterday when we introduced convnets, which talks about synthesizing image classes. So remember that when the convnet analyzes an image, it gives us a prediction. It gives us all the activations of the convnet with respect to that image, including the very last layer of classifications. So a natural question to ask would be, instead of, what would happen if instead of putting in a real image, we put in a fake image? And in particular, what fake image would maximally activate a particular class label? So before I put the phone in front of the in front of the iPod, in front of the camera, and it told me there's an iPod. Well, it told me there was an iPod, but it also told me that, I think maybe it's all these other things too. So the question is, can you synthesize an image which would maximally activate the iPod class? And it turns out that you can. You can use this approach that had been developed by a few people maybe a year or two before, where you use actually a really clever approach that using the same method that we use to train neural networks, stochastic gradient descent, except instead of changing the weights to train the network's accuracy, you train the pixels to get a certain kinds of activations that you desire. So for example, if you want to make the neural network neuron for the hartebeest classification go really high, you might put in an image that looks like this. And this would be measuring cup, or ants, or starfish. And you see that they're really weird, but you see the features of starfish kind of coming through. You see the fins in the corners and stuff, and the ant heads are kind of visible here. This is bananas, right? You can see all the bananas stuff here. The parachute one, it looks like there's a person there, which is pretty neat because, no, we don't tell the network that parachutes have people hanging off of them. But if you give it enough images of parachutes, they usually have people attached to them, and so it kind of learns this representation. So that was the inceptionism stuff, and it looks, kind screws, right? That's another one. You could see the reads. That's kind of that's cool enough, right? But and there's lots of people who had been kind of experimenting with this for a year or two before that. But what Deepdream did instead was it applied this technique to real images, to change real images or real photographs, so as to get more of the activations that it found. So let me describe what's happening here. So you have this picture of, I guess, these hartebeests in the African savannah or something, and what you do is you pass it through a neural network, and then you look at its activations, and then remember that the low layer activations, like the first or second layers, are looking for things like edges or gradients, things like that. So it'll find a particular distribution of activations of these edges, and you can use this technique to change the pixels of the image so as to amplify those activations, so as to make more of them. So the network thinks it sees these edges here and there. How do you make it see more of those edges here or there? And this is the kind of images you get, and they look really cool, right? You get these kind of interesting edges and features and gradients and lines and so on. It's pretty neat. Now that's at the low layers. If you do it at the high layers, and you can just give it a picture of the sky or something, it begins to like hallucinate weird weird objects like fish and dogs and snails and all of the different image classes that it knows. And so this technique called Deepdream. It was made by these guys, and it kind of set the internet on fire. So like in July last year, when machine learning was kind of becoming more, let's say on Twitter or Flickr and everywhere you can post media, the internet was just full of these. How many people remember this? Like remember watching? Yeah. One of the researchers who worked on Deepdream at Google named Mike Tyka, he did a lot of the early, like really cool artistic experiments with this technique. So he did lots of interesting things where he, for example, would, instead of using an image, he would just start with raw noise, just give it white noise to the network, and continuously sort of feed it back to itself and hallucinate these features, and you would get really, really wild kind of psychedelic art that looks like this. These are sort of low resolution images. And he also experimented with like different video techniques that I'll show. I'll just show some of the pictures that I made. This is Vishnu. And you just like get wild puppies, slugs, and dogs, and just kind of crazy features. You see the repetition. Monet, Egon Schiele. I want to go through these I want to flip through these kind of quickly. I probably included way too many. This is just some pictures of fireworks. And the thing is, you can actually get different kinds of images by rather accentuating the higher layers. As you see here, these are kind of high layers because you see the actual objects, or low layers where you see the edges and gradients and stuff. This is just basically vacation photos of mine. And this is more eye candy. This is Leonardo da Vinci. So, so Mike Tyka worked with these experiments where he would continuously crop the image and kind of generate more and more of this sort of eye candy. And it has this aesthetic, right? It's kind of inescapable because the Deepdream aesthetic is very well known, but you could get you could tease out some different kind of performance out of it. This is a class visualization that was done with the Deepdream software by Kyle. I mentioned Kyle's work yesterday. Kyle visualized all of the classes in Deepdream. So this is kind of, we were just looking at this in the Inceptionism class viz. So this is basically the same thing. And he kind of, he introduced some nice like regularization techniques so if in the middle of the iterations you would apply like a Gaussian blur, and then it would look a little smoother because the Inceptionism ones that we were looking at look kind of like a little jagged. So you see all the classes that are in here, mostly dogs and stuff. killer whales. Another attempt at the same thing. I think this one's going to be a little smoother. And this is some, again, Mike Taika doing really like, he kind of took this stuff to the next level. He made a bunch of class visualizations, so pelicans, leatherback turtles, and started getting into my nightmares. Okay, so really quickly about style transfer. Actually, before I show you, let's really quickly back up, and I'll tell you Deepdream software. So there's a few ways of doing Deepdream type stuff. You can do it. First of all, there's just online services that do this now. So you can just Deepdream on the website if you want. But if you want to use the actual software, you can still, I think it's still working, Google's original Deepdream repository. This was the original one from a year ago. It hasn't been updated much. It may by now actually be out of date because it was using Cafe, and maybe Cafe has undergone a few revisions. Cafe is also a pain in the ass to use. But also you can Deepdream. The way I would recommend doing Deepdream stuff is like with Keras, actually, because there's a good example of, and I mentioned Keras is one of the nice frameworks you can use to make some of this stuff a little easier. And one of the examples that comes with Keras is like a really, really straightforward code sample that shows you how to Deepdream. So this stuff, and there's probably other implementations that I'm not even aware of. So if you're interested in using this technique, there's lots you can do with it, right? There's different neural networks that you can use. There's different models that have different classes and different features, so you can tease out different features from the network. People have been asking a lot about like a Deepdream of audio. So that's something that we've been asking about since last year, and we're really not yet much closer to it than we were before. I think maybe in like another year or two, you might see this kind of stuff happening with audio, because wavenets are kind of here now, and those are really the sort of most recent thing that's been kind of nice for audio generation. I'll mention style transfer, and actually I'll be talking about some of this stuff tonight for those of you who are staying, so I'll kind of try to go a little quickly through this stuff. So style transfer is this technique where you regenerate an image in the style of another image. So like you take the Mona Lisa and you restyle it in a Cubist, Picasso, or a Van Gogh, or a Monet, this kind of thing. And the paper for this came out last August, so about a year and some change. The original paper, and really it kind of came out of nowhere. I don't know if a lot of people were really thinking too much about this. Like Deepdream was sort of an obvious thing because there had been research precedent leading up to it of the class visualization. But style transfer is kind of a curveball, and none of us had ever really seen this. And I remember when this came out the first day, I was blown away. I hadn't even thought about the possibility of this kind of thing. That was maybe when it hit home, like, okay, we can really make some crazy visual art with neural networks. And what they did, this is like this was made in Germany at the University of Tübingen. So they took, this is like a photo of their university, and they restyled it as Starry Night. And even this isn't that good looking. There were independent implementations that came out within a week or so of the original paper. Including one that I end up using a lot by Justin Johnson at Stanford, which is called Neural Style, and that's still actually pretty well updated. That's in Torch, using Torch. So if you look up neural_style, or actually neural-style, that's the Torch implementation of neural style. I've used this a lot, and there's a few others in Python, and they're really, really nicely done. I think this one is even better than the paper. And neural style, I'm going to explain sort of how it works, which is kind of a neat trick, which once you get it, it actually makes a lot of sense. Because if you look at the paper, there's all this math, but the math is actually not too bad. And I'm going to kind of describe how this works. So remember, like what I mentioned with Deepdream is that there's this sort of optimization that happens. So there's you start with an image of just raw pixel noise, something like this. And you use gradient descent to adjust the pixels through iterations to optimize a particular loss function. So the loss function with, or rather, well, Deepdream is a little different actually. That's just adding the gradient to the activations. I won't get into the details, but with style transfer, the loss function is this. I'm going to describe what this is. You're trying to come up with a set of pixels which minimizes this loss function, and the loss function is the sum of two separate loss terms. In principle, there are variations which attach like extra terms that deal with regularization stuff, which I'll kind of mention for those who get interested. But the main thing that it's trying to do is minimize the content loss, which is a sort of dissimilarity in the content, and I'll put quotation marks around content of the content image, which is here the Mona Lisa, and the output image, which is being generated here, right? And the other loss term is the style loss, which is the style, the dissimilarity in style, which I'll put even more quotation marks because that's even weirder, between the style image and the output image. And the thing is, we've already seen these activations, right? So I showed you in the convnet demo what these are. This is when you pass you pass this through a neural network and you can observe all the activations, right? So the idea with the content loss is actually really simple. It's just the difference. It's just like the distance between these and these, the activations of the output image and the activations of the content image. So you subtract this from this, and then sum it together, and the closer they are, the lower the content loss is. The style loss, is this too much detail? Maybe. But it's interesting, right? For those of you who are more sort of mathematically minded. So with the style loss, it's kind of weird, right? So what they do is they calculate what's called the gram matrix of of the activations at each layer of the network for all of these images. And what the gram matrix does is it takes every single one of these activation maps, every pair of them, so like it takes this one, and it calculates their correlation. So that becomes one element in the gram matrix, and it does this for every single pair. And it does that at every layer. So there's a gram matrix at every layer. And then basically the style loss is the difference between those. So the idea with style loss is the more the correlations, the more, so it's very wordy. So the more the output images and the style images correlations of their individual activation maps are the same between the two of them, then the lower their style loss is. And so you do this kind of process where every iteration it updates the pixels to make these losses a little lower, and then you get this. The intuition is, and this is kind of the easier explanation, is that if you look at these activations, it seems as though the content image and the output image, you can kind of see like the Mona Lisa's form coming through these. And that's the idea. Like if they have the same form, it'll have a low content loss. But with the style image, you see that these have like a similar textures. So this is kind of similar texture to this. This is a similar texture to this. This is a similar texture to this, and that kind of made sense to me when I looked at these, sort of under the microscope. Yeah. Yeah.
Why the grammatics is used only for the style and not for the input image?
Why the grammatics is used only for the style? Because if you think about what content is, content losses, it's just trying to make sure that every part of the image spatially has the same content everywhere as the output image. So it's really like you want to see these, you want to just subtract the raw thing. Yeah, it's space dependent, right? And the gram matrices have like get rid of location. It's just a correlation. And it's an iterative approach, so it kind of goes in iterations and looks like this, right? It's kind of fun to watch. I'll just show you a showcase of these. I'm going to go through them really fast because I have a lot of them. But these are just all different paintings that I use, and you'll probably recognize a lot of them. And it works at so many different scales and layers. I'll be showing these again later. So Google Maps is the one that people usually. This one's of Berlin. Or sorry, is it Berlin or is it? Oh, it's London. It's London. Okay, there's a map of London. That's New York. Rosetta Stone, TV, noise. You can get rid of the content loss altogether and just make sort of hallucinatory maps or whatever, you know. So this is Google Maps being hallucinated. You could do these in HD. So this is a different, there's actually a different repository in Python called I think it's called Neural Artistic Style, which you can find I think Mike Tyka made a fork of a Python implementation of neural style, which lets you do them in HD. So you can make these at very high resolution. They take a long time. So this is just like different versions of that. So I started doing this with video, and you can do it frame by frame. So like, this is just the first approach to doing frame by frame style transfer. And so it's kind of flickering a lot. This is like this animation by Mr. Div and Gustav Klimt's The Kiss. And you can also interpolate between them. So all of these features are available in the neural style repo. So this lets you like mix and match different styles. And then, so you can interpolate between them. So you can kind of weight different styles. You can have multiple styles, basically. And also you can transfer style but not color. I think that's part of this repo somewhere. Maybe not. Yeah, it's somewhere. There's like a flag. So you can transfer style but not color. You can. This is like more just style transfer eye candy. So there's a scene from Alice in Wonderland. So you see it's like flickering a lot. And the way I tried to reduce that was, because it's doing it frame by frame, would be to just blend output frames into input frames, or blend the output into the next frame that goes into the network. But then you would get these sort of ghost trails and not really reduce the flicker too much, but it would help tease out the features in sort of the same area. But then a few months ago, there was a repository that lets you do this on video at the same time. So I'm going to show you this too, if you're interested, because now it's way smoother. You can see, because what it does here is then there's the third loss term, which tries to keep as low as possible of an optical flow, or basically try to keep the optical flow the same between the output image and the output video and the content video. So this is all just different versions of that. I always kind of come back to Google Maps. This is available. I'll show you that in a second. But you can, if you go to, it's artistic video. I forgot what it's called. Artistic video style transfer. Yeah, this one. If you go to Manuel Reuter, artistic videos, this is the paper and the code for doing video style transfer. I think it's the only one I know of, and it's also in Torch. You should know that these take forever to generate, because you're generating a style transfer for every single, and using the sort of optimization-based approach for every single frame. So it's really time-consuming. Those videos took like 5 machines, like 200 hours. To generate like a minute of video, so it's a lot of computation. So this is real-time style transfer. It's not as good, and actually, I have this installation I'll have next week at like 20 frames per second, so it's much better. There are now, this is already out. I made this like 6 months ago, and it's totally outdated now, because now there's implementations that look much better, that actually do a much better job. You see there's all this like weird noise everywhere. So we can let's like show you guys. Hello, everybody. And also, the original thing I called this was cubist mirror. So I'll show that style. There we go. It's cubist style. Okay. The frame rate the frame rate. The reason why the frame rate is higher here is because it's using a slightly different technique. which was introduced actually by Justin Johnson, basically trained another neural network to map directly. Actually, when we looked this morning at the image-to-image neural nets, so it's kind of a special case of that. So it's a neural network that maps directly from the content image to the output image instead of using this iterative optimization approach, which means that it's almost like an approximation of what over many images the style transfer would do. And so it's faster, but it's not as good. So if you've ever used like Prisma or any of those style transfer apps, you're going to see it now. I think pretty soon on Facebook. I think they've been experimenting with style transfer for Facebook Video and Facebook Live, and I'm sure Instagram will have it soon on all them. And they are the reason why they can do it so fast is they're using newer techniques that have been. It's amazing just how much progress, because a year and a half ago you'd have to wait 15 minutes for one of these to cook, and now they come out in a couple of seconds and they look almost as good. And I think Prisma, I haven't confirmed this, but I think Prisma does it on the phone, like on the client side. So the mobile device is actually doing it. So it's really impressive how fast this stuff goes. So the thing is that, and this ties into what I showed last week. All of these are like kind of special cases, or at least with style transfer, it's a special case of an image-to-image neural network, which is to say that it's like an image which is generating, it's like a mapping between one image and another image that's learned by a neural network. And it turns out that there's a lot more special cases, and I'm going to just show you some of them from the research. And almost everything I'm showing you is research from the last 6 months, pretty much. Really, really new stuff. So one is a colorless style transfer. So this transfers the style, but not the color. So it kind of just takes, if you make a cubist, but keep the sort of original colors, which turns out is kind of a little trick that you can do the style transfer. This is a technique called neural doodle, which has been sort of in a few places, and there's different flavors of this. So I'm showing you kind of one, but that was made by this guy Alex Champagnard. And what this lets you do, this is kind of what we were looking at today. So one of the cases of the pixel-to-pixel software that we looked at lets you kind of make these doodles, like using a few colors, and it will transfer this from it's like an analogy. So it takes this original image, which might be a painting or something, and you segment it, doing what's called a semantic segmentation, which kind of segments it into coherent objects, like these are the rocks, whatever. And then you draw another image manually, let's say, which has the segments placed in different places, and it will generate a new image which has that same style, but it has shifted to the new segments that you've created. So you can create these sort of analogies. So it's really, really crazy, I think, this stuff. And Alex made a tool called Neural Doodle that lets you do this. So it's an application that you can download. This image I put in 6 months ago, and it was really funny back then, and somehow it's not so funny anymore. But yeah, this is the same. Sorry, it's illegal now. Yeah, it's a hoax actually. So yeah, this is an analogy of where we replace the mouth. We basically replace the mouth and eyes, so it just kind of shifts it over. Okay, so you can do super resolution. This is like a repository that, and this is when I put this again. This was like the only one that was on GitHub now. Now there's tons of them. This is like all over the place. Super resolution. So this lets you upsample. So you take small images, let's say, and then you do upsampling on them, so they look better. And the way that a software package like Photoshop or GIMP would do this is using some sort of a resampling method, like a bicubic resampling or something like that, which would try to smooth it. but it turns out that you can use a neural network to do it much better. And this particular one is called Waifu 2x. It does like ×2 rescaling, and I think it's optimized for like vector files support, like Illustrator files or whatever. So you can kind of see. I don't know if you can tell the difference. It's like a little bit cleaner. But there are other ones that are doing super resolution at the like on more pixelated stuff, which look really good. And so super resolution is another, again, image to image mapping, right? So small image to big image. This is some software called Stylit. This is a video that I downloaded. So watch carefully what's happening. This is an assistive style transfer tool. So here it's like, you can basically see what's going on. I don't even have to tell you. So you draw something simple, and you give it all of the sort of you draw something simple, and you give it all these contours and shading, and then it takes a more complicated image that you drew before, and it makes an analogy. So this is being produced automatically to have the same sort of character as as you would see here. So it's really neat. So again, this sort of analogy stuff is really nicely done. What's going on here? Am I missing? Oh, yeah, color. Okay. I guess I got rid of the colorization stuff. Fixed the colorization slides. So this is some baby. You don't need to know who this is. So suppose you have only black and white images. You can do colorization. So just for full disclosure, this is me. So all my images are black and white, even though I'm only 31. So I bet most people who are my age have color photos of themselves, but I don't. So I've been hoping to colorize my baby photos very soon. This didn't work very well with this, but actually today maybe this new software does a better job of this. So colorization, image to image mapping, wave nets. So let me just think. Let me really quickly look at what I put in the slides. I wanna save stuff. Who's staying tonight? Are people? Everyone? Okay. Yeah, I'm just gonna skip this because you're gonna see it later. I wanna show this to everyone because everyone's gonna love the WaveNet stuff. So I'm just gonna skip this for now. Let's just keep talking about. Yeah. Okay. Let's get into generative models and talk a bit about these. Actually, there's really not too much more here. So there's autoencoders, generative models. Maybe what I can do is, you know what? Let's kind of switch gears. I'm going to talk about these tonight, but instead what I'll do is I want to include, maybe we can talk about recurrent neural networks now. Or let's see, how are we doing at time? It's 5:10 right now, so what if I went for another like 20 minutes? Does that work? Okay. How about this? I'm gonna change this. I'm gonna get rid of this and this and this, and we'll gonna introduce recurrent neural networks because it's recurrent neural networks are something more practical that I think I'd like to talk about now while we have time, because it might actually affect some of your projects and things like that. Because this is another class of neural networks that we haven't talked about at all. So, okay. So, and we'll save the eye candy for tonight. So recurrent neural networks, we haven't talked at all about these yet. So, and I'm going to give you a very bird's eye view of these. So all of the neural networks that we've looked at so far, with fully connected layers and convolutional layers, all of those neural networks can be called what are called feed-forward neural networks. And what that means is that you start with information at one end, and you do a forward pass, and it projects through each of the layers of the network, and then you get something at the other side, right? So basically, you start with some input vector x, and it goes through the network, and it gets multiplied by a bunch of weights in a sequence of layers, and then you get some output vector y, right? All of our networks do that. That's all. That's basically all supervised machine learning is, right? Now, with recurrent neural networks, there's going to be one new feature added, which kind of changes everything, more or less, which is that recurrent neural networks, rather than just being feed-forward like this, they allow how do I put this? So they allow sort of sequence their hidden state, right? So something which is kind of analogous to the weights is allowed to change, and it changes every time an input goes through the network. So it allows basically information to flow back into itself. So here, in feed-forward neural network, all the information goes through, and then that's it. And it's kind of static, right? So if you pass the same image through this multiple times, it'll give you the same output every time, right? Because the network is sort of static. A recurrent neural network is not static. It actually changes its internal state every time you pass in a new network. And the way that's done is that instead of having just weights, you have this sort of hidden state, which is a function of weights. Like it's determined by weights. But the hidden state is changed by both the input vector and the previous hidden state. So let me show you how that might be structured. So this is a feed-forward neural network, all the things that we've seen, right? But in a recurrent neural network, you might get something like this, right? So maybe the architecture stuff is kind of too much detail for the moment. But instead of having, like one set of weights here, you kind of have two sets of weights which which multiply the input vector and the previous hidden state, and then they sort of get added together into the new hidden state. And that gets thrown in through another set of weights, and you get an output vector y. The reason why this is kind of important is what it allows us to do is to make sequences. So the network kind of goes through time and it becomes a sequence. So here, let me actually, so this is what we have in the first step. You have this hidden state at time 0. You input a vector and you get an output vector. And then at the next time step, this is the same network, the hidden state is actually changed, and it's a function of the previous hidden state. So the previous hidden state has kind of come and changed itself, basically. And then you get a new input vector, and so therefore you get an output y vector, which is a function of sort of almost a different network. The hidden state has changed, and so it's a different network. So you get this sequence of inputs, right? And the sequence is not commutative. So when you put in an input vector, it will change the hidden state in a certain way. When you put in another input vector, it'll change that hidden state in a certain way. And it's not like in reverse. So if you put in A and then B, it's not going to be the same as putting in B and A. So order matters. And since order matters, therefore it can be conditioned on sequences. So for example, like a really simple example is, let's say you want to make a text which predicts or even generates, basically predicts sequences of characters, like English language characters. So the way you would do that is you can imagine you can take text and you can divide it into all of the individual characters, of which we have, let's say, 27. All of the letters, there's 26 letters, and space. So you can turn that into a vector, which is just a vector of all zeros except a 1 for the letter that it stands for. So H is all these zeros and 1 for H. And then you pass it through the network, and it will generate some output vector. It will predict the next letter. E, let's say. So if you want to train it on hello world, right, you would do this. You would basically say, okay, remember with training, you're giving it a series of inputs and outputs that you want to map, right? So our inputs would be, so if you want to make a neural network which predicts the next character in a sequence of text, your inputs and outputs would be sequences of like one character and the next character. So predicting H to E, you put in an H, and you're training it so that it produces an E, or it predicts an E, right? So E to L, L to L, L to O. This is hello world, right? So we go from all the way through the sequence of characters, and you train it this way, right? So this is the whole thing being looked at once. So H E L L O. WORLD, right? So you're predicting H to E, E to L, L to L, and so on. So if you do this and you train it, you get at the end result is a neural network which can predict sequences of text, of sequences of characters to make text. And it's actually not just using a vanilla recurrent neural network, but it's using what are called long short-term memories. I'm not going to talk about the details of this right now for many reasons, but these are kind of the best recurrent neural networks that we've really sort of come up with so far. They're called LSTMs, and they're been really prominent in all sorts of applications. I'm really talking about all this stuff really fast, but a really, really great place to start if you're interested in these is to read this blog post by Andrej Karpathy, which you can find if you just look up unreasonable effectiveness of recurrent neural networks. This is a blog post that Karpathy put up about like a year and a half ago about recurrent neural networks, which talks about this in much more detail. And he made software in Torch, the same Torch that I've mentioned a few times, which that basically lets you train large corpuses of text to train character prediction models. So here, he trained it on the Shakespeare's entire corpus, right? So this is all Shakespeare. Why Salisbury must find his flesh and thought, that which I am not apps, not a man and in fire, to show the reigning of the raven and the wars, to grace my hand reproach within, and not a fair our hand, that Caesar and my goodly father's world. I get it? It's all fake. I didn't mention what's happening here. So like he trained an LSTM on all of Shakespeare so that it could predict, given a sequence of characters, what the next character might be. And it gives you like a probability distribution of what it thinks next character would be. So you sample from that probability distribution and then put it at the end and then sample it again. You predict the next character. And you get all this like really weird looking Shakespeare, like fake Shakespeare. So it looks like Shakespeare, but if you read it for long enough, it doesn't make any sense, right? But the cool thing about LSTMs is that you can train it on anything that can be represented as a sequence, and these are all just sequences of characters. But compared to other methods which can also sample sequences, like for example, what are called hidden Markov models. So Markov models are also these statistical structures which are good for generating sequences, probable sequences. But with LSTMs, they have this sort of like memory. They have a weird internal memory which learns to sort of remember things at a longer term. So for example, here you see it's trained on XML. So you just downloaded tons and tons of XML. And it remembers to close tags. So it has like the page tag, and then it has the end page tag, and revision and end revision. Right? It has all this. It creates all the spaces and tabs automatically. So it's really, really like yeah. I mean, you can see that it has this like really uncanny ability to remember things really well. It can even be trained on code. So one of the things he did was he trained it on the entire like source code of the Linux kernel. I think something like that. Yeah, this is the Linux. So this is all Linux. It looks like Linux, right? But it's totally fake. And no, it will not compile for anyone who's interested. But it does remember things like it remembers braces. It remembers to close braces and things like that. And it makes like kind of silly mistakes. But like I think one thing that I'll do is like it will use variables that it never declared, like seek equals 1, or it will declare variables and never use them. And all this kind of stuff. And one of the funny things is watching the presentation with him, and he mentioned how if you look at the actual Linux source code, every file has the entire GNU GPL license written on top of it. So like the actual license, it's really long, a couple paragraphs, I think, on top of every file. So this learned whenever it would generate a new page tag, it would recite the entire Linux GPL at the top of every page, like the entire by heart. So it's kind of really neat. Another thing they did, again, the same Justin Johnson who made the style transfer, they trained it on math papers. So if you guys have ever seen math papers, like the way you create figures is using this this sort of, it's not a language exactly, but like this sort of markup language called LaTeX. Are you guys familiar with it? It's like, it's spelled like latex, but it's pronounced LaTeX, and it just makes fake math papers. These are all like totally fake figures and fake formulas. They don't mean anything. But they, and like, you, who would know, right? If you've ever seen like a theoretical math paper, they're like insane, you know, which has a non-zero morphism. We may assume that Fy is a finite presentation over S. We claim that OX is a scheme where XX is of S such that OX maps to O. It's like, it makes up its own like nonsensical like figures, just that don't mean anything, right? OX is a sheaf of rings. This is clear that G is a finite presentation. I think one of the really funny ones was that it wrote like lemma 3. This proof will be omitted or something like that. It's just, can't remember. Recipes. So you can. This is online. This isn't just some GitHub gist. Someone trained it on a big data set of recipes, like text of recipes. And so if you read these recipes, you know, it'll list all the ingredients. It makes no sense at all. Like Chinese meat of 2 or salad. And then it's like, okay, chocolate, medium potatoes, chopped onions, vinegar. It almost makes sense. Like, I think it's like making a curry. You know, potatoes, onion, vinegar, sesame seeds, lemon juice, tarragon, soy sauce. Okay. And then when you start reading the recipe, the instructions, it just starts using ingredients and never listed. And it doesn't make any sense at all. So, you know, when ice cream can be softened dumplings. So again, this used to be funny, but it's no longer funny. The Donald Trump Twitter bot. I think, I showed this, didn't I? I mentioned, okay, you guys already saw this, yeah. Did I show the dense captioning stuff? I'm gonna show this tonight, actually. So I'm gonna skip this. And I showed it to a few of you. So this is also worth knowing. It's made by the same people, Karpathy and Johnson, and Fei Li at Stanford, the computer vision lab. So this is some software called DenseCap, which creates captions of. You can look it up. DenseCap. It's over here on the GitHub presentation. Oh, sorry, GitHub source code. So what DenseCap does is it. Let's actually, oh, maybe I can just results fig. Yeah. So what it does is it captions images. So here you see like, it's a neural network which will find objects. Like, okay, this is sign on the wall, right? Man wearing a white shirt. It's more beige, I think. But this is a white laptop on the table. This is a man sitting on a table, and I think it's a woman. But anyway, man wearing black shirt. These are all men, actually. Apparently, no, this guy's a man. Man wearing blue jeans on the ground. Chair is brown. This is a trunk of an elephant. Man wearing a black shirt. So you see like what's going on here. And the cool thing is that these captions are actually novel. So they're not taken from a data set. They're actually produced by a recurrent neural network. It's not using characters anymore. It's using word tokens, but it works basically the same way. What it's doing, I don't have. So I guess I didn't include that picture. What it basically does, just to give you like a really bird's eye view of the way it works, is that it's using a recurrent neural network and the convolutional neural network. So recurrent neural networks, I remember I mentioned, well, the kind that I showed is kind of a simple one where the hidden state conditions itself, but you can make sort of more complicated architectures. And one kind of recurrent neural network, you can allow it to, let's say, be conditioned by so its initial input vector would be the activations from a convolutional neural network. So you would take an image, you would pass it through a convnet, it would take its activations and pass it through, and then it would produce a sequence of words which is conditioned on convnets activations. So that's more or less how it works, and it's trained on a huge data set. So they trained it end to end on I forget what data set they used. I think it was MS Coco, which is this data set that you can find online that Microsoft compiled, which is something like 80,000 images, which contain 3 million captions. So they had people look at images and make squares and write down what they see. So these are actual. You can download it. It's available. It's a huge data set of captions and associated images. And so they trained this architecture to produce new sequences of words, which are likely to come from a certain set of activations. So so really cool. And and the software's online, and it works really well. It's on Torch again. And actually, you can download the model, and it takes just takes like just a couple seconds to do do the generation. So you can create real-time installations. I have one of my students in the class that we did at School of Ma made this really awesome installation where he put a camera inside of a little box, and it was during our final show, and it was it was tracking people kind of coming in through the space, and it was using DenseCap to take a picture and caption it. It would give you all these captions, like you can give you as many as you want basically, and he had a like a natural language parser parsing through it and looking for haikus. So haiku is any poem that's, what is it, like 5 syllables? Five. I think it's 3 5 3. Yeah, 3 lines, but it's like a number of syllables, right? I forget what the exact. It doesn't matter. So he found the haikus, and then he would print it on thermal paper. Is this really elaborate kind of installation? It's really nice. So yeah, this is available. I'm going to show you some of the things that I did that later. So I'm going to skip these. But I'm just going to quickly give you a rundown of some things that LSTMs and recurrent neural networks can do. And not all of this is just for you to be aware of the research, because part of this is not just applications, but it's good to be aware of some of the frontiers of the research. And actually, some of this does have software online, and where I know that it does, I'll try to remember to say something about it. This is called semantic object parsing. Or sometimes it's called semantic segmentation, which is, I guess, more or less the same thing. What it's doing is it's taking an image, and then it's parsing the image into its sort of parts, right? And you see the parts are colored analogously. So there's two people here, and their torsos are both green, their heads are red. So you're kind of getting analogies of different parts, and actually, Fabian, right? We found a repository the other night that does this. I forget, you have the link, so you can share it. Right? That does something. Well, not quite this. I don't know if it provides analogies like this. Does it? It just does the segmentation. Okay. It's related technique, right? It segments things, because if you use something like, let's say, like a lot of you have used OpenCV, right? OpenCV contour tracking is really sort of naive. All it does is it looks for like homogeneous blocks of pixels, but it doesn't segment things into like what you would call semantic objects, which is like an object which would be classified as a coherent thing, like a person, right? So semantic segmentation is a way of parsing out actual objects, coherent objects, in spite of superficial changes in the sort of color or whatever, the blobs. This is so LSTMs. So I mentioned LSTMs can predict characters of text, but really LSTMs and recurrent neural networks can predict sequences of anything that can be vectorized. So so for example, you can train an LSTM to handwrite. So all handwriting is a series of vectors moving a pen around, right? So you can, if you predict that sequence of a sequence of vectors, you train it on another sequence of vectors, right? And you train it, and it learns how to, move. It learns how to predict new sequences of vectors, and this can be used in other ways too. So this is a project I've been wanting to try, just haven't had time, but make something that just learns from paths how to draw shapes and simple sort of. If you work a lot with vector graphics, this might be the kind of thing that you might get into, because vector graphics can be turned into all directions of velocities basically, and then you just predict new velocities. Now the cool thing about recurrent neural networks is that they can so because they can operate, they operate on sequences both at the input and the output level, and sequences don't have to have a length. So with convnets and feed-forward neural networks, we're sort of stuck with a particular size of input and output. But with recurrent neural networks, we can have sequences because you can keep sampling from it as much as you want. And so there's all these architectures that take advantage of this. Actually, the one I wanted to show. Oh, I should put in language processing. Okay, yeah, I'll get to that in a second. This is generating images from captions. So we talked about image to caption. Well, this is caption to image, and this is I guess this is from a year ago now. So maybe it's been superseded. But here you can be like, okay, I want a picture of a stop sign flying through blue skies, or a toilet seat sits open in a grass field. Yeah, so right now it generates really small images, but I think this is the kind of stuff that I think this is within the next year. You'll probably see this take it to the next level, because we have really, really great generative models now, like from generative adversarial networks and these deep generator networks. I'm going to talk about those tonight, which generate synthesized images, which are very realistic and not so low resolution. So these are very low resolution, but I think you can probably leverage those ones to make very high resolution. What's up? Oh, we should stop. Okay, let me just see if there's anything more important that I should. This is a really awesome project you guys should check out, made by this guy David Ha, who took a data set of handwritten or not handwritten, but I guess vector graphics of Chinese characters, and he trained it to produce new fake Chinese characters. These are all vector graphics files, so these are all fake Chinese characters. Oh, I showed that. Did I show it the other day? Yeah, I did. Okay, all right. Okay, that's enough of that. I should really show you guys the language processing stuff, but I guess I can kind of save that for tomorrow. Is there any questions? Any questions? Talk about what? Sorry? Reinforcement learning? Is that what you said? Oh, so maybe that's something. So with reinforcement learning, I suspect we won't be able to do anything very practical with it, or at least maybe some simple things. I mean, but I was gonna maybe include that as another. If we have time, one of these, I can talk. You want me to talk about it now, or probably not now, right? Yeah, yeah. So I think maybe tomorrow we can do a little segment on reinforcement learning. Reinforcement learning is pretty fun, because it's we'll talk a little bit about very theoretical stuff, like super futuristic, artificial general intelligence, which I guess I mentioned that Monday. But for now, I guess it probably won't be something that we can do very practically. Not something that we can do very practically. So probably, we can kind of deprioritize that. I think we want to prioritize stuff that's more practical, I guess. But yeah, we can definitely talk about that at some point, maybe quickly. The other stuff that's left is I wanted to maybe include some slides about just contemporary sort of societal and critical issues and current events. It's been really interesting, because actually just the last few weeks, there's been a ton of news. I think especially because of the election that just happened in the U.S. Just a lot of people talking about the role of AI in things like fake news and echo chambers, and how different political groups talk to each other. So it's been really, really just the last few weeks. So I think it might be interesting to include something about that as well. And those are kind of the last things that I sort of have left. So yeah, we can kind of figure out how to factor those into the next 2 days. So I'm gonna turn this off, and then we have like I guess I'm starting around 7 or whatever. So between now and then, we can kind of like like do what we were doing before this, just kind of break out into groups and just keep working. Oh, really? Okay, so that's not really possible, but we can talk. Yeah. Yeah. Okay. All right. Cool. All right. I'm gonna stop now.